Hey, everybody, welcome back. It's another day and it's another episode of Everything is a Spring. Derek, how are you, buddy?
Hey, Jim. I'm doing pretty good, man. Happy to be back. Apologies for the week off. I wasn't feeling up to code, but we're back.
Hey, it's all good. I'm glad you're feeling better. And, we're back with another great episode. I think I've got a pretty good one for us today. I guess I don't really have a whole lot of preload topic. Derek, let me ask you a question, right? All right, let me ask you a question. I've got a pretty good preload topic for us today, I think.
What we got?
Have you ever done whippets?
I've never done whippets. I'm actually really afraid of whippets.
Why are you?
Biologist.
Okay, explain, please.
Well,
fill us in.
we went to college. People did some wild things, right? And power to you. But like, whippets is one of those things. It was so easily accessible. You're really just starving your brain of oxygen for a small amount of time to get a bit high, right? If that's your thing, fine. You do it safely. But it's like whippets is one of those things, the line in the sand between, oh, this is fun or whatever, to actually medically dangerous is so thin and it's hard to recognize, like with other things when you've drunk too much, when you've done too much pot, like if you're doing harder drugs, there's a really fine line in the sand, but it's usually pretty night and day. I mean, you could just take a nap, and if your O2 level's too low, you could have some really serious, like, brain damage in a small amount of time, and it really does cater to kids, because, like, these are the same kind of canisters we used to use in, like, air gun, like, back in the day, like a Daisy air gun. But now it's, I think you need a license to get that from the pharmacy, and compressed air,
I think you have to be 18 to get that stuff now, but I don't know if this was just me being naive about drug use, but I always thought whippets were called whippets because you used like the cans of whipped cream.
That's so innocent.
Right?
I would rather it be that.
Because the whipped cream is charged with nitrous oxide, which is what you can use it to get high, right?
Yeah. Interesting. I'd rather it be whipped cream,
Like, I feel like that would be better, because then you also get the whipped cream.
You get a little tasty treat.
Exactly.
But no, I haven't done whippets. That's a weird thing to be kind of afraid of, but I am afraid of doing whippets, and I worry for my friends if they ever did them,
That's fair. Yeah, and it's interesting, right? Because nitrous oxide, which is the propellant for whipped cream, and also it's basically like laughing gas, right? It'll knock you out. So it does have medical uses, but one of the I don't know where I was going with that. I'll be honest.
Well, I mean, to be fair, we were talked about a little bit about nitrogen-based gases last week, right? And the one we were talking about, isomethocyanate, right? Yes, it has
methyl isocyanate.
Methyl isocyanate, thank you. It's got a very reasonable boiling point, right? As it gets warmer, it's not going to turn to a gas as readily as other nitrogen-based gases we might be more familiar with. So, in one of the Gen Chem experiments we did in college, there was like a really clear label on the like SOPs, like, hey, don't inhale this gas because you think it'll get you high. What it's going to do is turn to liquid in your lungs. And I've always remembered that because I thought to myself, why did they put that in the SOP? Someone in the 80s or 90s was just like, hey guys, listen, we're going to get this nitrous oxide and huff it down. And no one was like, well, nitrous oxide isn't brown. It shouldn't be, right?
Yeah.
So I'm guessing somebody in the past, they were like, yeah, let's get down on it. And sure enough, turn to liquid in your lungs. Now, knock, knock, open up the door. It's liquid acid in your lungs. And that's not a fun time for you or your doctor.
No, that is not good. I find that, like, I always find it funny to, like, talk to the people that the rules are made for, right? It's
I would love to.
You run into people every now and again where it's just like, yep, they're the reason why we can't have fun anymore.
Yeah. And it's not always their fault, but isn't it often?
It is. I feel like often it is. Because, it's just kind of like, why you huffing the gas in the chem lab?
It's
But
like, don't huff the
also,
gas.
you know, it is what it is.
Yeah. And you get a lot of that in construction, right? Like you go on a construction site and it's just like, hey, odd rule, but our architect or chief engineer told us, hey, when you're doing I-beams or whatever and you're moving them, don't take pictures. And it's just like, that's a weird rule. Like, why wouldn't we be able to take pictures? Like, well, Jim wanted to get an I-beam photo from underneath it and, the rest is history.
The rest is history. Yeah, don't go under the suspended loads. Like, that's a pretty big one.
That's a great shirt.
Don't walk under suspended loads. That would be an awesome shirt.
That's a great shirt.
We need to make that shirt.
Dibs.
Because that would be a beautiful, that everything is a spring shirt.
Yeah, I got some interesting stuff for a merch drop, but I won't delay us further, Jim. Like, why would you ask me about whippets? That cool.
Well, you see, the thing is, Derek, today's episode takes us back to December of 2016.
Oh, snap.
When there was
future.
It's the future. Yeah, so in December of 2016, there was a shortage of aerosol whipped cream in the United States. And unfortunately, December is the time in which the most amount of whipped cream is being consumed because of the holidays.
Really?
Can you guess why there may have been a shortage of of whipped cream around Christmas time in December of 2016?
Well, I'm going to guess it was those crazy kids.
It was them crazy kids blowing up they blew up a air liquide nitrous oxide facility.
Wait, really?
In Florida.
Oh, yeah, I thought it was the kids because they were doing whippets. They committed an act of domestic terrorism. It's a little bit of a jump.
Well, they wasn't intentional, but those pesky kids,
in their facilities.
Those pesky kids over at Air Liquide.
Oh, we're talking gas today.
We're talking gas explosions again today. And basically their nitrous oxide plant in Florida, I believe the city is called Cantonment, Florida. So it takes us back to August 28th of 2016. That is when the explosion actually happens. But it impacts the Christmas season, which is probably why it made headlines.
Interesting.
So at approximately 12:10 p.m., a nitrous oxide trailer truck exploded at the Airgas manufacturing facility in Cantonment, Florida.
Sheesh.
The explosion killed the only Airgas employee present and heavily damaged the facility, halting nitrous oxide manufacturing at Cantonment indefinitely.
Wow. Unlucky day to be the one guy on the job.
Yeah, not a great time. But we'll get into how this happened and why it was that he was where he was when the explosion happened. Because we've got, I think this is an interesting episode because it gives us an opportunity to talk about some, I think are some interesting engineering fail-safes for handling explosive gases. So let's talk a little bit about nitrous oxide. Derek, what do you know about nitrous oxide?
Not much more than what you've already said. It has a common use in dentistry, right? You can use it as a anesthesia, right? Or at least back in the day. I mean, it's a step up from ether. It'll make you a little loopy. You've seen the videos online of like folks coming off of their surgery and they'll be real goofy and real lighthearted and, generally harmless if administered correctly by a professional, right? Yeah. As you mentioned before, some people have found, we can just kind of get this in small doses out of, different types of enclosed canisters. I think early compressed air was mixed with nitrous oxide for a while. Right. Other industrial uses, not too sure. Besides, like you said last episode, pressurization, right? You could use it as a thing to differentiate pressure in tanks, especially if you have a liquid container. So it's everywhere.
So it's a very common chemical. It's used in a lot of different industries. It's actually one of the things that makes it really useful is it is very compressible. And then also it is, well, so in the case of whipped cream, for example, it actually it dissolves in fat, right? So it's highly soluble in fatty materials. So that's why they have it in the whipped cream, is because um, as you're propelling the whipped cream out of the can, the nitrous oxide is actually basically boiling out of the cream, and it's causing it to foam up at a very, very high volume. So it's like 4-to-1.
Oh wow.
Whereas if you were to use air, it would only be a 2-to-1 expansion for the foam. So that's why they use nitrous oxide in whippets, and also they use it in food kind of processing production fairly regularly because it's inert, right? Well,
Right.
well, it's not inert, but
I mean, it's got an
it
oxide
prohibits.
component to it, so it might be
It
flammable.
does. It is actually very not inert, but it prohibits the kind of like rancidification of food. So it's used
Okay,
in
so
whippets as
preservative.
well. It's a preservative as well.
Well,
Um,
Jim, about the like canister thing, right? Just for our international viewers, because I know like we think of like canned cheese, canned whipped cream. We're not talking about like the Cool Whip you get in a tub, right? It comes in a
no, it's
can.
aerosol.
You
It's
know,
like an aerosol
you
can.
tilt the little tube, like exit hole. I don't even know what you call it, dispenser, and
Nozzle, I guess.
nozzle, right? You move it over a little bit. It lets some air release, like Jim said, pushes the food product out while also whipping it nice and good on the way out.
Whip it.
Whip it.
Whip it good. Um, but nitrous oxide is also used very widely as a propellant. And the reason for that is that obviously it has a oxygen atom in it. And the nitrogen atom is relatively, so nitrous oxide is 2 nitrogens and an oxygen. So the N2 part of that is not like super well attached to the oxygen, because N2 is just gaseous nitrogen, basically, which is stable. And nitrous oxide is not very stable. So it doesn't take a lot of energy to break it apart. And then the nitrogen also doesn't inhibit combustion. So that's why it is very useful as an oxidizer, both in like rockets and also in vehicles, right? Because you'll have, you'll like throw on the NOS, right? Like for the Fast and Furious or whatever, right?
Oh yeah.
And it's basically because the the um, the nitrous oxide is stored as a compressed liquid, and so as it evaporates, it cools down the air charge going into the engine, and so that makes the air more dense, which gives you more oxygen. But then when you burn everything, the oxygen from the nitrous oxide gets released as well, which adds more oxygen to the fuel mixture. So you can really throw a lot of fuel into the vehicle, into the combustion chamber.
So you
And
get this
that's
like two-piece
why
combo of efficiency. You're doing two
it
things at
is.
once.
It is. And originally this was developed by like so many other things in rocketry and combustion. It was developed by the Germans in World War II. It was Nazi
Oh,
technology.
of course.
Um, and they were basically, what they were trying to do is they were trying to use it to uh, make their aircraft fly faster at higher altitudes, because the higher up you go, the less oxygen there is in the atmosphere.
Right, less
Which
oxygen you can feed into your engine.
Exactly, which means that you can't put as much fuel, which means you can't make as much power. So yeah, so there were some interesting applications for that. Um, but again, like kind of the problem with nitrous oxide is that when it gets hot, right, because it's not very stable, when it gets hot, it tends to spontaneously
Combust.
separate. Yeah, and then that's an exothermic reaction as well. So it can cause itself to chain react, basically. And that is exactly what happened at the Airgas facility on the 28th of August, 2016. And so that's called a nitrous oxide decomposition, basically, is when it gets hot enough to spontaneously decompose. And what that basically does is it introduces a very large amount of free oxygen into the environment. And Derek, free oxygen is extremely dangerous because it promotes combustion so well.
Oh, yeah.
Yeah. So basically, what happens is the employee at the nitrous oxide facility was filling up a tanker, and tank filling is an interesting process because basically what they've got here is you have the nitrous oxide, or excuse me, you have the nitrous oxide storage tank, and then you have a pump, a transfer pump that moves that nitrous oxide from the storage tank into the trailer.
Okay.
And then you also have a return like vent line, basically to allow the atmosphere inside of the trailer to then come out and go into the nitrous oxide storage tank so that you don't have a vacuum
Right.
that could implode something. So the way that they have their transfer pump set up is they basically have the tank, and then it comes out to a ball valve so that you can turn it off or on. And then it goes through a Y strainer. Do you know what a Y strainer is?
I don't. Is that just like a splitter?
Kind of. So it's basically like it's kind of like a T. Here, I'll send you a picture of it. So one of my sources for this is actually the CSB final report, which is kind of cool.
What's the CSB?
The CSB is basically it's like an engineering. It's the Chemical Safety and Hazard Investigation Board. It's a federal agency. That basically this is what they do: is they investigate accidents like this. But anyway, yeah. So that's kind of neat. Is we're using
actual investigation report data. That's exciting.
Yeah.
I had to make sure I drop that in the sources.
But yeah, so this is what a Y strainer is, and it's basically you have a straight piece of pipe, and then you have a piece of pipe that kind of comes off at a 45-degree angle to the direction of flow, and you have a wire mesh, basically filter that goes in that, and that basically just helps filter out particulate because you don't want contaminants in your nitrous oxide because that can be really bad because those contaminants might be flammable, and if the nitrous oxide decomposes and then catches that on fire, that can lead to a propagation of the flame. So that's why you've got that. Yeah, so then you've got that Y strainer, and then you've got the actual transfer pump itself, and then you have another Y strainer, and then you have another ball valve before it goes into the trailer. So nitrous oxide, as I said before, can decompose explosively, which will basically yield N2 gas and oxygen gas and a lot of heat. And part of that problem is you can accidentally set that off if there is heat generated in the system.
Right.
And one of the problems with these pumps that they were using is that if they were to be run dry, right, or which is to say that there would be no nitrous oxide moving through it, because all this nitrous oxide that we're talking about right now is stored in liquid form, ideally. Right, but the other thing about that too is like as you're pumping into an empty trailer, there's no pressure in that trailer to begin with. Does that make sense?
Makes sense. Is that why you're venting the atmosphere too, so you can keep a pretty reasonable pressure gradient?
Exactly. Well, that's why you're looping the. So that's why you have that second hose that goes back from the trailer back to the storage tank, is so that you can have that pressurized system. Because you really want your nitrous oxide to be a liquid because it's more stable that way.
Right.
And so one of the dangers of filling nitrous oxide tankers is that initially when they're empty, there's no inhibitor of a potential decomposition reaction, right? Because basically there's no fluid pressure pushing back on it. Does that make sense?
Okay, so the gas has more Well, this is just something we learned, when things evaporate, right? Like, it's the difference between having the cap on your Coke tight, the cap on your Coke halfway, and the cap off, right? That gas is going to escape as it boils one way or another, in this case, carbon. The less pressure you have, the less likely the gas will get out of liquid form.
Okay, yeah. So basically, the nitrous oxide as a liquid it's obviously like there's less surface area, right? So if you're trying to burn something like even gasoline, actually, this is a great example, is gasoline, right? So your gasoline engine isn't actually, you're not trying to like have a puddle of gas in your combustion chamber. You actually try to aerosolize the gas. So if a flammable gas is aerosolized, the flame is going to propagate much, much faster. Whereas if it's liquid, it may not propagate at all. With nitrous oxide, basically the same is true. So if you have a liquid nitrous oxide, that will prohibit the flow, that will prohibit the flame from propagating because there's just not enough surface area to cause that combustion. Does that make sense?
It doesn't make sense, because the gas form is like filling the combustion chamber in this example. That's the surface
Correct.
area problem you're talking about.
Yeah, so gas has like a lot more surface area. Yeah, right, there's more exposure of that stuff.
Yeah.
And then the other thing is that when they're filling these trailers, you're actually filling it from the bottom of the tank, right? So the tanker, basically, you've got a hose that goes into the very bottom of the tanker. So that way, as you're filling it, that liquid nitrous oxide is going to be on top of the opening. So even if there was to be a fire that happens in the filling tube, it wouldn't be able to propagate into the tanker because it's submerged in liquid nitrous oxide.
Makes sense. It's a buffer.
It's a buffer. The danger, though, is that when your tanker is completely empty, there is no barrier, there's no liquid nitrous oxide insulating that tanker from a potential explosion. And because because the pressure in that tanker is relatively low, the nitrous oxide is going to be a gas. And that is a recipe for explosion. So that's the very dangerous part about loading trailers with nitrous oxide from completely empty. And there's actually some recommendations that you're supposed to leave a little bit of nitrous oxide in the bottom of the trailer to prevent that.
So as you're filling it up, it's not truly empty. You still have a slight buffer level.
You would still want a little bit of buffer there at the bottom. So the problem here, what they traced this back to is the transfer pump. So the transfer pump can actually generate heat because you have components that are running into each other, basically, because this is what's called a positive displacement pump, which means that for every rotation of the pump, it displaces a specific volume, which is determined by the geometry of the pump design. And so basically, like there's actually there's elements that are actually making contact. Let me give you a picture of a positive displacement pump.
Exciting. And I guess in what you say, since you can engineer these pumps to displace a certain amount of liquid per second, it makes it easier to measure, right? Like you can measure based on rotations.
That's exactly right. And that's like the really big advantage of these pumps. And there's a bunch of different types of them. I believe the one in this Airgas facility was a gear pump, an external gear pump. So you can see that one is present on this little picture I've shown you. It's the top left. And these are great pumps because, again, they produce a very consistent flow depending on how many revolutions you're making. The problem with it is that you have direct metal-to-metal contact. So if you run them dry, if they're run dry, they can generate a lot of heat really fast as that friction builds up.
Okay.
And so you need the liquid through the pump in order to cool everything down. And that's a really dangerous thing when you start talking about flammable gases. And so one of the things that is really important is to not let that pump run dry, because the heat generated by the pump can actually cause the nitrogen or the nitrous oxide to reach its decomposition temperature, which then can create a chain reaction.
Oh gosh, so and it leads back into our conversation about activation energy. We talked about two things that really drive reactions to run faster and for much longer, and that's more reactant, which you're saying you have since it's a decomposition reaction, and heat. An exothermic reaction works as a catalyst for the next reaction, and it kind of loops into this feedback loop.
Exactly. And because the nitrous oxide decomposition is a very exothermic reaction, it just feeds into it even more.
Right. And for our friends, like, exothermic gives off heat, you know. You are an exothermic reaction right now.
We all are. Unless you a snake.
Snake endothermic reaction. They can't get enough of that heat.
So because of this, the CGA basically they're the people that make kind of the regulations and codes for the gas industry.
Oh, it's big gas?
It's big gas. Yes. So they require that these loading pumps for nitrous oxide have an interlock that prevents the pump from dry running. Basically, if there's not any fluid flowing to the pump, it should shut down immediately.
That's a good design.
Which is good.
Safe.
Exactly. And then in addition to that, they also require that there be flame arresters on the front and back side of the pump. And that's what they were using these Y strainers for. So, Derek, do you know what a flame arrestor is?
I have a loose idea, but I do want to hear the professional definition for sure.
So, a flame arrestor, which is also called a flame trap in kind of more colloquial nomenclature, it's basically a specifically engineered set of openings that allow the gas to flow through, but they prevent the flame from traveling backwards. Right. So basically, what it does is it creates a zone of heat transfer where gas that's moving past the flame arrestor is basically cooling the flame arrestor down, and then the flame arrestor is pulling that heat away and dispersing it out of the system, so that any hot gas in front of it, which is potentially combusting, can't go back through the flame arrestor. Does that make sense?
Oh, okay. It's like it's making a pressure gradient intentionally.
Not a pressure gradient, but a temperature gradient.
Temperature gradient. So it's literally just making sure heat doesn't transfer back into the tank. You have a venting situation.
Exactly. Right. So it prevents the heat of that combustion from combusting gas behind it.
Interesting. It's like a firewall in a way.
It is. It is like a firewall. And also like a firewall, eventually they will heat up and then it will pass by it anyway, because they're basically, if you do have a sustained combustion on one side, it's only going to buy you some time.
Right.
But they are very useful as safety devices, and they come in all kinds of different shapes and sizes. But one of the kind of key things about the flame arresters is that the thermal, like the heat transfer and the thermal dynamics, it's very complicated. And so you really have to have it designed specifically for this purpose, right? So and you really have to test it, is really the only reliable way to make sure that it's going to work, is you have to test these things.
So you couldn't just slap a flame arrestor from a nitrogen tank onto a O2 tank. They have to be engineered separately.
They're completely different because it's a different gas. And then you also have to look at your operating conditions, so like what's your temperature range of operation? What's your flow rate for the gas that you're using? I mean, all these things factor into it.
So there might be different equipment for like the northern United States compared to the south just because of ambient temperature changes?
There certainly could be.
Specific?
It could be. Now, I think that you could design, because even if you're talking about like just ambient temperature, you're talking about a temperature swing of maybe 100 degrees, 120 degrees Fahrenheit, which in the grand scheme of things is not like that much. But yes, I mean, so in theory, you could have different equipment for the South or the North or winter and summer, in theory. In practice, I think you'd be able to design a flame arrestor that would work in 30 degrees Fahrenheit, and also would work in 100 degrees Fahrenheit. So I think that would be excuse me. I think that would be a solvable design challenge. But yes, in theory, different gases are going to require different flame arresters. Different pressures are going to require different flame arresters, et cetera, et cetera. And again, I want to clarify. I want to be very pointed about this. They require real world testing in order to get right. And so what they did at this particular Airgas facility is, in order to make those flame arresters, quote unquote, flame arresters, they took those Y strainers and they packed it full of steel wool.
Okay.
And the idea there is that as the gas is flowing through that steel wool is going to basically serve to pull heat out of the gas. The problem is, Derek, have you ever started a fire with steel wool?
I was about to say, Jim, a little background on both of us. We were both Boy Scouts, right? We know how to set something alight. And one of the things they teach you is with just a bit of a spark from a 9-volt battery with the 2 terminals on one side, you can touch that to steel wool and get a pretty steady flame. And then the steel wool kind of acts as a kindling and tinder for you right off the rip. If you have juice in that batteat.
It does.
So you're saying
and
a
that's
spark.
because basically that steel wool, when you heat it up, it oxidizes. It starts reacting with the oxygen, and the steel wool is thin enough that it burns.
Right.
Basically.
And it's very aerated. Like it's a mesh. It holds a lot of air in it.
Yes. There's lots of surface area for it to combust. So the Airgas people are like, okay, well, you have to use stainless steel wool or brass steel wool.
Okay, that makes more sense.
That would make sense. But unfortunately, the operators on the ground just used regular steel wool.
Oh, like what you can get at Home Depot.
Yup.
Oh.
Mild steel wool.
Dude.
So that's not good. The other problem with the steel wool Y strainer flame arrestor is that it's really hard to test because getting the steel wool to compact evenly and consistently is extremely difficult. And as we said before, the only way to make sure a flame arrestor is going to work is to test it. In order to have a reliable flame arrestor, you just have to run these tests. And they never did. They didn't do it.
Really?
And they didn't do it. They knew that they needed to do it, but it never happened. And so what ends up happening, and then the other thing about this particular facility is that in order to get the gas to start, basically, in order to start the transfer of the nitrous oxide, there is a panel that you have to, basically the operator has to be at, and they have to press 2 buttons at the same time to basically get it going. So because of the pump design and the design of the system, what you have to do to get this particular Airgas nitrous oxide pump moving is you actually have to bypass the dry run safety lock.
Okay.
Because you have to prime the pump, right?
Okay, makes sense. Oh.
The problem with that, as you might imagine, is that you're bypassing the safety device that's specifically designed to shut off the pump if it's running dry.
Well, Jim, you know what? I have an idea. We'll build a warehouse, fill it with cotton balls, right? And steel wool.
Yes.
But the only way we can power it is if we turn off the fire suppression system every day. It'll be fine.
It'll be fine. And so what ends up happening, and there should be another safety. This is another thing too, right? Is there's supposed to also be a safety mechanism in place that if the pump itself gets too hot, it shuts down as well.
So redundancy.
But that safety measure is not in place at this particular plant.
Oh, shoot. So the pump is the problem, start to finish. It doesn't have the safety device it needs.
Correct. And it's a design that can produce enough heat to ignite the nitrous oxide. Or rather, decompose the nitrous oxide, because it's not actually a flame, it's actually a decomposition.
You're just making yourself into a more flammable product. Very casually.
So basically the safeguards that were ineffective is the flame arresters because they were never really tested, and yeah, the flame arresters are really tough because they have to be designed so specifically that if the operating conditions change, they may not work anymore anyway. So it's a very challenging thing, but the best way to figure out if it's going to work or not is to test it. And Airgas never did.
Out of curiosity, Jim, if you know, how long do you reckon it would take to test that?
I mean, right, so it's going to depend, but like basically what you're going to have to do is you're going to have a testing setup, and then you're going to have to test different, basically styles of flame arrestor until you get it to do what you want. And the danger there too, right, is that you actually have a potential explosion when you're doing the testing, right? So the testing has to be done in a very controlled way as well, because if the flame arrestor doesn't work, the flame is going to travel back down the tube that you're trying to spit that flammable gas out of, and that can cause a problem.
So you got to have
testing
a quick
is
hand
non-trivial.
you have to have a hand on the kill switch for this, even the test.
Correct. And really what you should be doing is using remote switches and stuff like that. So you're not actually anywhere nearby the storage tanks or whatever.
Oh, that's what that control panel's for? It like puts them on the other side?
Well, so that control panel, actually no, this control panel is in the worst possible spot.
You're kidding.
So this control panel is basically directly in between the tank that they were filling, the tanker that they were filling, and the the filling station. Okay, so do you see those like yellow cones, basically?
Yeah.
Or not cones,
like the
but
barriers?
Yellow barriers, yeah. So this is a top view of the facility. And you can see that the that kind of green roofed building is the actual like storage tanks, basically.
Okay.
And then, or the station, the storage tank station or whatever. And then the star in the first picture I sent you is where the operator was. And then, do you see all those tankers?
Yeah.
So there's supposed to be 2 more tankers to the left of them.
Oh.
And then, yeah, that star is basically, where those yellow barriers are.
Oh.
So in order to start the gas filling, you have to be standing directly next to the tanker.
So you're between the source tankers on the ground and whatever truck and tank you're filling with at this transfer pump. So you're between a gas and a gas place.
Yes.
Dude, that is...
Yes.
I know that there's probably one of those situations, like there's no better way to do it until something like this happens. Like it's just not a problem. But that had to be nerve-wracking, right?
I would imagine... Well, but I think like what it is again, it's this complacency of like, okay, it doesn't nothing happens and nothing happens, nothing happens. So you just keep doing it. And then eventually like something, like it's Murphy's Law, right? Like something's going to happen.
And when it does...
I don't know.
I mean,
like when it does, and when it does, you're standing right between it.
You fill your car with fuel like once a week. Most people in America, once or twice a month at least, right?
And you're standing right between the gas pump and your car,
and all of the lines underneath it, right? It's just one of those things you never think about it until like someone across the way is smoking a cigarette. You're just like, what?
Exactly, right? Like, and that's like the reality of it is. Okay, well, you look at it from like a efficiency standpoint or whatever, or like a convenience, right? Like people will literally put their lives at risk for the most tiny convenience.
And companies will absolutely put your life at risk for a tiny convenience. We're not going to pay you an extra 10 minutes to walk over there, run all that cabling, phooey.
Exactly, and it's just, I think it's just human nature to not want to do the work, and I understand that impulse, like
we're, believe it or not, human. Yeah. Like work gets monotonous at times.
Yeah. So why would you, and then you have to think about it too, is like, okay, well, am I going to be walking another 30 to 100 feet, and your whole job is to fill these tankers, right? So you're going to be filling, there's like 8 tankers there that they're to fill, right? So that means like every day you're walking an extra like 800 feet, so
Just
over
back and
a
forth.
course of a week, you're doing an extra like couple of miles,
Sheesh.
but again, like it's not that big of a deal, but you know, we are the way that we are sometimes. And so people, I think, tend to not want to do that. But anyway, so the flame arresters were basically just cobbled together and never really tested. So that's not good. So you can see here on the left, it's basically there's like a wire mesh tube, and then the steel wool just gets rammed into it and packed.
And the
And you
idea
can
is it
see,
filters out particulate?
well, yes, but in this case, they're also trying to use it to soak up the heat from the combustion,
Gotcha.
or rather from the decomposition, to prevent that decomposition reaction from continuing down the tubes into the tanker or into the nitrous oxide storage unit.
So in this case, for this reaction of, the decomposition of nitrous oxide, they're trying to raise the activation energy by moving that heat as a reactant away.
Exactly. That's exactly what they're trying to do. They're trying to starve the reaction of heat so it can't react.
Yeah, taking away the catalyst. Okay.
That's
I'm on the same
that's
page.
exactly what flame arresters are supposed to do. What they're supposed to do is they're supposed to get that heat away from the reaction so it can't continue. That's exactly right. But obviously that doesn't work because they used standard steel wool, which can actually act as a combustion element because it's reactive. So these are some tests they did of steel wool burning. The one on the left is steel wool combusting in air, and then you've seen that before.
Right.
And then the one on the right is it combusting in an oxygen environment.
It is going off.
It is going off. And again, the problem is you're creating pure oxygen in this environment.
Like so you're making fuel for the reaction you don't want.
Exactly. So then the second failure mechanism is the run dry safety lock. And basically, in order to, as I said, in order to basically start the pump, you have to bypass the safety valve. And the reason for that is basically the delay is the pump has to be pumping 15 gallons per minute before the interlock is functional with this particular design. That's actually kind of a lot of fluid, 15 gallons per minute. And so what you have to do initially is you have to hold down two buttons at the pump start switch, which overrides the shutdown as long as those buttons are pressed.
Okay, so you can't just get on your phone. You have to focus on actually
you have to have both thumbs pressed into those buttons, basically. And then once you verify, because there's a flow meter nearby as well. So there's actually a mechanism that will tell you how much flow you have through pipes. And so when you can visually verify that the flow is greater than 15 gallons per minute, you lift your thumbs off those buttons and the pump runs. And if the flow rate drops below 15 gallons per minute, the interlock will then shut it down.
Okay. It's like a little Kickstarter, like a human-assisted Kickstarter.
Exactly. The problem is, there was no temperature protection integrated into that system. So if the pump gets hot, it could still be running and just be running very hot.
You're monitoring flow rate, and you have a shutdown for that, but there is no thermometer-based kill switch.
Correct. And the interlock has no redundancy.
Oh, so that's just it.
It creates a single point of failure, which is not good to have. And then the other thing too is that the interlock for that safety is most important at the initial stage of filling. Because you have the nitrous oxide vapor, especially when it is immediately, when the tank that you're filling is completely empty. The danger of running that pump dry is so great because any decomposition will immediately spark off and then propagate into the tank. And then once it hits the tank, it has so much room to expand that it becomes an explosion. And that's what happened here. And you can see, I mean, by the photos, it's absolutely destructive, and the facility was damaged for significantly. Obviously, there was loss of life, and it's pretty tough.
It is. And it's one of those situations, like, there was significantly less, I would say, safety concerns immediately prominent in this one compared to when we talk about something like Bhopal. We can see that regulation, at least this one's in the United States, you can see they were at least regulated, but it does sound like they kind of just checked the boxes this time. Oh, we'll put your flame. Ooh, I forgot the word already.
Flame arrestor.
You'll take your flame arrestor, install it, but they never tested it. Like they checked the box of, yeah, we got flame arrestors. We have one on each valve, but you never actually got actionable data, which, if that's a part of the SOP, I mean, what's a fire suppression system that's never been tested in 15 years? It's a coin flip.
Exactly. And as part of this, because this is actually part of the CSB report includes other similar accidents in the past. So this is not a one-off thing. There's at least 4 other recorded incidents like this where basically the pump causes the heat and that sparks off a nitrous oxide decomposition reaction leading to an explosion. So it's not like there are not ways to get around some of these and to do some of this stuff more safely. You can have different pump designs. You can have different ways that what you can do is you can recirculate nitrous oxide through the pump so that if you are no longer filling the tank, you basically shut off the valve that you're filling to, and then that nitrous oxide will just recirculate back into the storage tank.
Okay, so you got a similar cooling loop in a way.
Yes, exactly, right? So there's always fluid moving through the pump, even when you're shut down. And then you turn off the pump, and then you can shut the ball valve from the pump. So there are ways to do this, and it just goes to show you like how easy it is, I think, to get complacent, and how easy it is for that to be really deadly, you know. And we have to. What I see this as is like, how can we design systems such that complacency doesn't result in danger?
Right. And another thing we didn't really touch on much, that, full disclosure, I've worked at a facility like this. It was just a different type of gas. Luckily, mostly non-flammable gases. To think of one person on site, and that's I'm guessing the person who's like moving the truck out. That is a huge level of responsibility on one employee with no oversight, right? So, imagine he does everything right except for he's sleepy from the drive, Anyone can make a mistake on their own. It's nice to have 2 eyes on each problem for multiple reasons: accountability and someone else to say, hey, that doesn't look right, in case you don't have to go off your solo judgment. And I'm guessing that's common practice. Guy drives the truck up to the facility, has the key, does what he has to do, gets on with it. The operating costs they save must be astronomical, not having someone on site all the time.
Well, I think this is just, in this instance, I don't think he's the truck driver as well. They just have tanks that are dropped off, and then they fill them.
Gotcha.
And then the trucks will come pick them up and take them away.
Right on. So he's just running the whole facility that day.
He's just running the whole facility by himself that day, right? Which also, I mean, I guess in a sense it's a good thing because nobody else got hurt. But also, yeah, it's like there should be more checks or some, again, like I think about this as a system, as a failure of the system. Like, why is the way to start the pump to disable the safety features? Like,
yeah, you're kickstarting the pump by disabling the safety feature. You're right. Like, in hindsight, it doesn't make any sense.
It's not a good system. Yeah, that's not a good system. Like, the way to start your system should not be to disable the things that keep your system from exploding.
Right.
It just, again, it goes to show you, it goes to see again, when we're designing systems as engineers, we have to be thinking basically along the lines of a mistake will happen. at some point, somebody's going to make a mistake while using this system. How can we design this system such that when that happens, it doesn't create a dangerous situation?
Right.
And that wasn't accomplished here, right? So, like, to me, that is a failure of the system design.
And it's reasonable to say that, too, because we're in the modern day. This is 2016. That's what, 8 years ago, give or take? A little more?
Geez, yeah.
Something to think about, right?
Not quite 8 years, I guess. Come August.
I wonder how the safety mechanisms changed since then, if ever, or if the regulation changed, because you got to think a human-based fail-safe is really no fail-safe at all in the modern day, right?
Correct. There's
no one else monitoring. There's one guy on site, and rip that guy, because it's not fair to him. He's just doing what he was trained to do over and over again. And for a fact, the company probably, most likely, absolved themselves of some responsibility by saying it's the operator's fault, because he's not there to tell his side of the story.
That is fair. I think the CSB, the CSB does, so in reference to like the recommendations or whatever, the CSB does kind of create some new recommendations to both the company Air Liquide, which owns the facility, and then also the industry as a whole, right? And so some of the suggestions that they make are to basically, like, you actually have to test your flame arresters. And you have to have these dry run safety interlocks that can't be overridden in order to start the pump, right? And then the other thing is that you have to provide warnings and provide your workers with the knowledge of the history of these accidents. So there are some suggestions that are made from the CSB and kind of like updates to code, essentially, that come out of this. And, hopefully we won't see this type of accident again.
Yeah, gotta be smarter every day. But, it's unfortunate because we're going to see it time and time again with engineering, right?
Yep.
The hindsight's 2020. Regulations are written in blood. Hypothetically, if this situation happened and the guy survived, right? Let's just say he was far enough away or whatever. The same level of urgency on the regulation definitely wouldn't have happened because, there's a fine line where companies look at property damage versus loss of human life, as hard as that is a pill to swallow, is true. I mean,
yeah.
If it's one person, they're not going to treat it the same as if 400 people and the town downwind got affected,
That's very true. That is very, very true. But yeah, so that is the Airgas explosion at Cantonment, Florida, on August 2016.
In the modern era. Whippets. Don't, alright, fair disclaimer, don't bypass your safety mechanisms, and also, don't do drugs.
Don't do drugs. Don't do whippets.
Kids should not do drugs. Strong
whippets,
opinion.
not even once.
That sounds like a Dare commercial from back in the day.
Whippets, not even once.
You wouldn't download a gas canister.
Why would you put it in your body?
No, but we hope that you learned something on today's episode of Everything's a Spring. I'm going to keep working on getting better so we can make sure we're busting out weekly uploads, but I don't think this will be nearly as much of a beast to edit compared to
yeah, this one, I tried to keep this one to a reasonable length. We're at about an hour and 2 minutes right now.
Yeah.
Which I think is a more reasonable amount of time.
Yeah,
so
it'll probably get chopped a little bit,
A little bit of chopping to do. Derek, got anything for us to plug?
You know what? I don't have a product to plug, but I just want to talk to our audience for a minute. Audience, I'm plugging you. This year, it's January. It's not too late to make a decision for yourself. Take care of yourself out there. Learn some engineering. And, of course, more important than all of that, tell us what you think about the podcast. Let us know. You sat here with us for an hour. Surely you're hooked at this point. Why would you do that, man? But if you do, send us a comment. Send us a like. There's multiple ways to get in touch with us. Twitter @AllOurSpring. You like that transition there? Self-care to caring about your friends and everything is free. Everything is free. No, what you got to plug, Jim?
Yeah, no, please. I mean, if you enjoyed the podcast, please leave us a rating and a review either here, I guess wherever you're getting your podcast. It really helps us out, both on Spotify and on iTunes. And I don't know anything about the other podcast apps, quite honestly. But, those are really, really helpful for us. And again, if you do have anything that you'd like to share with us, any comments, things you'd like to see in the show, please let us know. This is kind of... I'm still interested to see where we kind of evolve, right? Because this is definitely still an evolving show in terms of our format and in terms of our content. So let us know what you think. In addition, I'll plug my business, Whiskey Grail, the white oak drinking vessel made to mimic a bourbon barrel, charred on the inside to help smooth out your whiskey and enhance your drinking experience. Check us out at www.whiskeygrail.com and find the holy grail of the whiskey drinking experience.
Ooh, I like that. Now that's a t-shirt.
That's a t-shirt. So, Derek, I think let's bounce.
Let's bounce.